All right, welcome back. Mr. Richardson here with lesson 13.5, reaction spontaneity. So spontaneity means that the reaction will happen. The example we have here, we see a picture of a boat kind of sitting in some water, and it's rusting. It's very rusted, and it continues to rust. The thermochemical equation for rusting is iron plus oxygen yields rust, iron oxide. And here is the amount of energy that is produced per mole. So any physical or chemical change that once it has begun occurs with no outside intervention, for example like rusting, this is what we consider a spontaneous reaction. Again, once it's begun is a key. Again, think of lighting a piece of paper on fire. We have to get it started, but once it's begun, that paper will burn and burn and burn until the reaction is complete, regardless of any outside intervention. So that is a spontaneous reaction. We could, of course, have the reverse reaction occur, where we go from rust to the elements iron and oxygen. However, doing this would also flip our delta H. Therefore, we would have an endothermic reaction, and it would not be spontaneous. This would not occur without outside intervention. So spontaneous and non-spontaneous, just because a reaction has a positive delta H, does not necessarily mean that it would be non-spontaneous. Again, that would be an endothermic reaction. Examples, ice melting at room temperature. This would be an endothermic reaction. It would have a positive delta H, but it's going to happen. Well, we all know this. There is something else playing a role. It's not entirely about the energy put into the system or released from the system. The other set of conditions are what we call entropy. Entropy. Why chemists use such similar words, entropy and enthalpy, is beyond me, but make sure you guys are taking a look and understanding the difference between enthalpy, which is change in heat, and entropy, which we are about to discuss. So entropy, symbolized by the S, and change of entropy would be delta S. The knot there tells us we're working at standard conditions. Entropy is a number of possible ways that the energy can be distributed. And nature has shown, studies have shown that nature prefers the maximum number of possible ways. A positive entropy change leads to spontaneity. So that's how you can have even an endothermic reaction happen spontaneously, because you have a positive entropy as well. You are increasing the number of possible ways that the energy in the system can be distributed. There are 5 factors, and you should be aware of all 5 of them. I suppose you could call it some memorization, but the more homework you do and the more you study, the more familiar with them you'll be without sheer memorization. But there are 5 factors that can determine or help to determine the entropy of a system. So first of all, the state of matter. So solid molecules, if you can envision a solid crystal lattice, those particles have very limited movement. Liquids have some movement, they can slide around each other, and gases are free to move pretty much wherever they want. Those little particles are bouncing off of each other and going pretty much wherever they want. So entropy increases as substances change from solid to liquid, and again from liquid to gas. Again, a solid particle is not able to move very much, so that's not a whole lot of places you can put energy. It's stuck. Liquid can move a little bit more, so the energy can be distributed in a few more directions, and gas can go pretty much wherever, so it would have the highest entropy. The second factor is dissolving of a gas in a solvent, so dissolving a gas in a liquid, and this is always going to decrease the entropy. So here's our example. We have gaseous oxygen. If we were to dissolve it into a liquid, probably water, we would have a negative entropy. So this would be a non-spontaneous reaction. Assuming no physical state occurs, or change in physical states, no melting, no boiling, the entropy of a system usually increases when the number of gaseous particles is greater than the number of gaseous reactant particles. So here's an equation. We have all gases. On the reactant side, we have 2 moles sulfur trioxide. And on the reactant side, we have 2 moles of sulfur dioxide and 1 mole of oxygen. Because we now have 3 moles of gas on the product side, but only 2 moles of gas on the reactant side, we're going to have a positive entropy. More gas particles means more ways to distribute the energy, so that's a positive entropy. Generally, when you dissolve a salt, an ionic compound, into a liquid such as water, we are going to increase the entropy. Again, it's almost like going from a solid to a liquid. So taking solid table salt and throwing it into water will have a positive entropy. And finally, when you increase the temperature, the random motion of particles, it doesn't matter if they're solid, liquid, or gas, the random motion is going to increase. Thus, entropy will also increase as temperature increases. Again, make sure you're familiar with these 5 factors that can influence entropy. There are some homework questions. The more you look over them, the more you think about them, the more familiar with them you'll become. All right, this leads us to what we call Gibbs free energy, the delta G of a system. At least G stands for Gibbs, so hopefully we can keep that in mind. Our negative enthalpy changes, again, enthalpies are delta H, lead to spontaneity. Our positive entropy changes, that's delta S, lead to spontaneity. So it's really, really nice when you have a negative enthalpy change and a positive entropy change. That one's very easily a spontaneous reaction. But what if both values are positive or both negative? So you're having an endothermic reaction, but you have a really high change in entropy. Or vice versa, you have a very exothermic reaction, but you're decreasing entropy. What then? Will the reaction be spontaneous or not? And that leads us to Gibbs' free energy equation, which allows us to determine if the reaction will occur spontaneously. Here is that equation. So here's our Gibbs free energy, delta G. Here's our change of enthalpy. And here is our change in entropy. Notice it depends what temperature it's going to be at, and that has to be in Kelvin. So always make sure you're converting to Kelvin, 273.15 degrees Celsius. So to calculate Gibbs free energy, we're usually going to have to make a conversion. So watch your units. The reason for that is our entropies are usually expressed in joules per Kelvin, and our enthalpies are usually just expressed in kilojoules. So watch what your units are and how to work with them one way or the other. In order to determine if the reaction will occur spontaneously, you look at the sign of your delta G. If you have a negative delta G, you'll have a spontaneous reaction. Take a look at a quick example. So determine reaction spontaneity for a process where the delta H is 145 kilojoules and the delta S is 322 joules per Kelvin. Is the reaction spontaneous at 382 Kelvin? So we have an endothermic reaction, but we do have an increase in entropy. So will this reaction occur spontaneously at 382 Kelvin? So a very warm temperature. Again, I like to list out my variables. It's not something you have to do, but I recommend you do it. I think it does help. We're trying to calculate the delta G, the Gibbs free energy. We have an enthalpy, delta H, and we have an entropy, delta S. Our temperature is 382 Kelvin. It's already in Kelvin. That's good. We don't have to convert it from Celsius. What we are going to have to convert is either our delta H, which is listed in kilojoules, or our delta S, which is listed in joules. We're going to have to make sure that those two units match up. To be perfectly honest with you, it doesn't matter which one you convert. I went ahead and converted my delta S joules into kilojoules. All right, now we can plug in our variables to get our delta G. And we find a delta G that is positive. So no, this reaction will not occur spontaneously. And now it's your turn for a little bit of practice.